Greetings. My name is Pierre Ohlmann. I'm a postdoc at University of Warsaw. And in this video, I will present my paper at CSR2022 entitled "The GKK algorithm is the fastest over simple mean-payoff games." First, what is a mean-payoff game? So a mean-payoff game is played on a graph, on a directed graph with edge labeled by integer weights. We have two types of vertices, vertices that belong to the minimizer and vertices that belong to the maximizer. These are drawn as circles and squares, respectively. I will use small n to denote the number of vertices, in this example 6, m for the number of edges, 13 here, and n for the absolute value of the largest weight, so here it's 8. So in the mean-payoff games, the two players alternate in moving along the edges of the graph, which produces an infinite walk on the graph. The aim of the player is to optimize the mean payoff. The mean payoff is defined by this formula. It is the average in the very long run of the partial sums of the weights. So on a picture, if I draw the partial sums, which I will call the profile of the weights in the walk on the graph, the mean payoff can be seen here. It is the average that you get in the long run. So technically, the limit of these partial sums may not exist, which is why we have to put a lim sup here. But this is a technical detail and does not really matter. We will also be concerned with energy games, which are defined in the same kind of graphs, but with a different objective or valuation, which is given now by this formula. So it's the supremum now of the profile. So on this run, the energy value is given by this peak of the profile. So note that the mean payoff is bounded by the value of the weights. However, the energy, it is always positive because the profile starts at 0, but it can be potentially infinite if the profile is unbounded. Okay, so let's go back to our example and try to study the mean payoff game. So let's assume we start from this vertex here on the left. It belongs to the maximizer. However, there is only one choice of an outgoing edge, which is this -8 edge. Now, from there, the minimizer has several different choices. He can either go to the right or go back to the left. When going back to the left, the minimizer ensures to cycle through this cycle of weight -2. So from this vertex, from this part on the left, the minimizer can guarantee to have payoff -2, the average in the long run. Now from this part on the right, well, the minimizer can either choose to go back here or to cycle there. Now, if the minimizer goes through this edge, he sees 2, and then the maximizer sees 1. So here the average would be 1.5. However, here the minimizer can secure average 1. So this is actually a better choice for him, right? So going through the green edge, the minimizer ensures value 1. And now from here, well, the maximizer, his best choice is actually to go there, and this gets him a mean payoff value of 1. Now what's left is the middle part. From this vertex, the maximizer can either go up here or go here to the left. Now we have seen that if he goes to the left, then the minimizer can enclose the game in this part, and we would have value -2. However, if we go up there, then it's a better choice for the maximizer, because now one can observe that the best choice of the minimizer is actually to go down there, and this gives value -0.5, whereas this was value -2. So putting all of this together, one will realize that in this mean payoff game, the optimal strategies for the players are given by the green edges. Okay, and the values are written here in green besides every vertex. Okay, so from this first example, what we see is that the optimal strategies, they do not really care about what happened in the past. The players can always play optimally by, from a given vertex, always choosing the same successor. This is a very important fact about MeanPayoff games. It's called positionality, that states that the optimal strategies in such games are this simple. They are always positional. It was proved by Ehrenfresh and Michalski in '79. Now, this is also true for energy games, that optimal strategies are positional. So let's try to look at this example now from the point of view of the energy game. Now the optimal strategy for the energy game is displayed in orange. From this top vertex here, the minimizer can ensure to never go positive in the profile. So since the profile will stay at 0, the energy will be 0. From this part here, well, the maximizer can ensure that the profile diverges to infinity. So the energy value will be infinite. And then if we look at the rest, well, from this point here, minimizer can either see 2 and then just see only zeros. So this choice gives him energy 2, whereas going there, he would see a 4. So this is the preferred choice that secures energy 2. From here, we have energy 0 because we see -8 and then 2 and then only 0. So this profile stays below the x-axis. And from here, well, maximizer should choose this edge to ensure profile, to ensure value 9, which is the best he can get, the maximal energy. Okay, so in this example, we see that, the optimal strategies for MeanPayoff and energy games may differ. However, these two games are still tightly linked because it remains true that from any vertex, the MeanPayoff value, which here is written in green, is non-positive if and only if the energy value is finite. So this is very easy to prove from the fact that optimal strategies are positional, because, well, if the players play the optimal strategies for the MeanPayoff game, then they will secure finite energy value if and only if the MeanPayoff value is finite. So that's not hard to prove. Another observation we can make at this stage is that whenever an energy value is finite, well, it is obtained by first having a small path and then cycling in a cycle, in a non-positive cycle. So the finite energy values are actually bounded by the number of vertices times the largest weight. And this is a standard observation. Okay, now one last comment on MeanPayoff games is that here there is a slight breach of symmetry because of vertices of value 0. We don't know if we should consider these vertices to be winning for the maximal player or the minimal player. And since we will be very interested in this talk about symmetry, we will actually make an additional assumption on the MeanPayoff game that the simple cycles never have weight 0. So this assumption is actually not satisfied on this game because of this loop here, but okay. So this assumption will be very important for us. I will call it the assumption, simplicity assumption. And it can be made without loss of generality. It's just to make the game nicer and our life nicer in general. Okay, so these are MeanPayoff games. And we will be interested in the complexity of MeanPayoff games. So the decision problems is actually to compute the set of vertices that have value non-positive or strictly negative. So this is the problem we're interested in, and it actually belongs to NP and to co-NP. The reason is again that the optimal strategies are positional. So a certificate of having a negative value is an optimal strategy for the minimizer, and this can be written in and verified in polynomial time. So this is in NP, and it's also in co-NP because of the symmetry of the problem. Negative instances have a good strategy for the opponent, which gives membership in co-NP. And the main open question is now whether this decision problem is in P time. Okay, so that's our setup. Now, what is known? There's two types of bounds for Mean-Payoff games. So we have known for a while, like 20 or 25 years, that these games can be solved in actually pseudo-polynomial time. And there are also some combinatorial bounds. So these are kind of two sides. So the best pseudo-polynomial bound now is this one. So number of vertices times number of edges times largest value of the weight. This is actually, so this was established by Brim, Chalupka, Doyen, Gentilini, and Raskin in 2011. This algorithm relies heavily on the link between Mean-Payoff and energy games that we highlighted on the slide before. It's quite a simple algorithm that we will call the value iteration algorithm. The best combinatorial bound is given by a randomized strategy improvement algorithm from Björklund and Vorobyov. So it's sub-exponential, but it's randomized. And we're rather interested in deterministic algorithms here. And the best deterministic bound is given by a recent algorithm from Dorfman, Kaplan, and Zwick from 2019. This algorithm here is an improvement of the value iteration, so it accelerates the value iteration. It's quite a fairly complicated mechanism that happens here. And in this talk, we will actually look at a very old algorithm, so more than 30 years old algorithm by Gurvich, Karzanov, and Kachian. And we will give a new analysis of this algorithm. And in particular, we will give a completely symmetric analysis, assuming that the Mean-Payoff game is simple. So no simple weight of, no simple cycles of weight 0. So with this analysis, we will get some new bounds. So we will have an improved pseudo-polynomial bound. I say that it improves the bound of BCDGR because this term here is always smaller than n times n. So what is this term actually? It's so n is the largest absolute value of the weight. And now E plus and E minus, well, E plus is the largest finite energy value, which we said is smaller than n times n. And E minus is the largest finite negative energy value. So we will see in a minute what this means. So that's our new bound. It's smaller than this in general, and it can be really smaller in many examples. We also have a matching combinatorial bound, which tells us that actually this very old algorithm was already state-of-the-art, also in terms of combinatorial bounds for deterministic algorithms. Okay, and now the main novelty that we really want to emphasize in this paper and in this talk is that this algorithm is symmetric, and the analysis we give will be completely symmetric. So that's really the nice part about this. So if we think about it for a minute, one of the main motivations for looking at Mean-Payoff games is that they belong to NP and to co-NP, thanks to their symmetry. But however, the algorithms that we knew, so all these three algorithms described here, don't exploit this. They don't exploit the symmetry. Or maybe this one does a bit, but not in such a clean way. However, here we completely exploit the symmetry. So that's really what's nice about this algorithm. So yeah, so in this talk, our emphasis will be on symmetry. And we will try to convey some intuition behind the bounds without necessarily giving complete proofs. Okay, so the main tool we will use is the tool of potential reductions. So this has been used also in the context of graph algorithms already by Galai in '57. It was for Mean-Payoff games. It was first introduced by in the GKK paper, and then it was also used later on, more or less explicitly for Mean-Payoff games. So it's quite a simple idea, which is as follows: a potential is just a map from vertices to integers. So for each vertex, I give some potential. And given a potential phi, we have a game reduction where we keep the same graph structure, but we just change the value of each weight as follows. The new weight of an edge from V to V prime is just the previous weight, and we add the value at V prime, the potential at V prime, and we subtract the potential at V. So on a drawing, if we have potential 1 on this vertex and 0 elsewhere, then the reduction will add 1 to all ingoing edges and subtract 1 for all outgoing edges. So that's the idea. And the thing is that if you do this, well, on the path globally, you will preserve the profile roughly. So what do we know about potential reductions? Well, first, we do not affect mean payoff values by doing such reductions. So this is quite intuitive, I guess, that in the obtained graph, well, the average payoffs will never change. So this is what it does to mean payoffs. And now for energy, it's a bit more subtle. And this is what we will really exploit in this talk, is what I call potential reduction theorem, is that if I apply the potential reduction with potential phi, and assuming phi is not too big, so I'm looking at phi being a positive potential that does not exceed the energy values in the game. Assuming this is satisfied, then the energy values in the new game versus the energy values in the previous game, well, the difference between these energy values is exactly given by phi. Okay, so the intuition behind this theorem, which is really not too hard to prove, is that this potential will just affect the very beginning of the profile, but then after this, it's going to be the same profile. So let's have an illustration of this. So here's our vertex set. So each of these points, they give the energy value for each of the vertices of the graph. So we have two types of vertices. There's vertices with negative mean payoff. So these have finite energy, as we discussed. And vertices with positive mean payoff have infinite energy. Now, also remember that finite energy values are always smaller than this threshold. So this is what our energy values look like. And now let's assume that we have a potential phi that satisfies, so it's positive and it's smaller than energy values. So it's something like this. And then what the theorem states is that if we apply the reduction corresponding to phi, then we get again G prime, and the energy in G prime is this difference here. Okay. So why is this interesting for us? Because this tells us, this gives a very nice technique for devising some algorithms. So what's the technique? Well, what we care about is computing these energy values. And well, if we can find a potential phi which is like this, so positive and smaller than energy values, then when we apply the potential reduction, then these energy values, they get smaller. So somehow we get closer to our goal. So if we just iterate this process, apply reduction and so on, then at some point we will end up matching the energy values, and we're essentially done. Okay, there's also a caveat here of, well, we cannot really match these infinite energy values, but if at some point we overcome this threshold, if we become greater than nn, then we know that the values have to be infinite. So that's a way to deal with this issue. That's actually what's done in the value iteration algorithm. Okay, so that's a way of doing some algorithms. But as I mentioned, we want to be symmetric. This is not really symmetric. So let's make everything symmetric. So here is where the fun actually starts. So remember, we had this valuation. We're interested in energy values. And now I want to emphasize that this is that this really looks at one player. So let me call this energy plus. So it's the supremum of the profile, remember? Okay, and now there is the symmetric valuation, which we will call energy minus, the dual energy valuation, which is the infimum. So the infimum in the profile, it's always negative or non-positive, and it could have also value minus infinity if the profile is not bounded. Okay, so we have these two valuations. And the potential reduction theorem really talked about this thing. So it tells us if we have a potential that is quite small, does not exceed the energy plus value, then when we apply the reduction, we know what happens. Now there's a dual version that talks about negative energy values. It's obviously proved in the same way. So it tells us if I have a non-positive potential, but that does not exceed in the negative negative energy values, then if I apply the reduction, I get closer to the values in the negative. Okay, so I have these two theorems. And now really what we would want to do is to apply a potential reduction that actually satisfies both of these hypotheses of both theorems. So this, when you look at it, it seems a bit hard to do because we want a potential that is non-negative, but also non-positive. So it seems a bit that there is a problem here because only the zero potential satisfies this, but the reduction is actually trivial. So what can we do? Well, we can still do something. If we realize that potential reductions are shift invariant. So what I mean by this is, if you take some potential and shift it, so you shift all the values by the same constant, then the reduction that you are going to perform will be actually really the same reduction as with the original potential, because all the differences are going to be the same. So what we will do is we will apply the potential reduction theorem to our potential phi. But the dual potential reduction theorem, we will apply it to some shift of phi. So the game that we obtain with the potential and the shifted potential, this game G prime, is the same. But now there is hope that we can apply both at the same time. Okay, so this is maybe the main idea here. Okay, so let's illustrate this on a drawing. So again, this is my vertex set. These are the positive energy values in my game. So they are finite for vertices that have negative mean payoff values. They are infinite for vertices that have positive mean payoff value. Now, if we look at the negative energy values, they behave similarly. So on this side, they are minus infinity. And on this side, they are finite and negative, or non-positive. And let's look at this green potential phi. And I claim that this potential is actually really nice. So why is it really nice? Because if I shift it, I can make it satisfy both the wanted hypotheses here. So let's look at this. Well, first, if I shift it so as to make it positive, so if I add this value, the same value everywhere, then you can realize that, so I will have a potential which is positive, and it will actually be smaller than the energy value. So it will satisfy the potential reduction theorem. So that's nice. But it's also true in the negative with this green potential phi. So if I shift it so that all the values become negative, then actually I will be higher than the blue values. So I also satisfy this dual potential reduction theorem. So if I now apply the corresponding potential reduction, then I can apply both theorems, and I know that I will get closer to both positive and negative energies. So the positive energy values in G prime will actually be smaller. So here, for instance, if you look at this vertex, the value we get is the difference between these 2 points, right? So these values are going to be smaller, and the same for this. So I will get closer to a game where the values are actually 0. And such a game, I can detect when the values are 0. So I can stop the iteration. Okay, so that's the idea. If I can get a potential that satisfies, so that is like the green potential here. So a potential such that by shifting it, I can satisfy both PRT and dual PRT, then I win on both fronts. I really get both positive and dual energies closer to 0, and this is a very nice symmetric algorithm. Okay, and the GKK algorithm does just that. So how does it? So now I need to find such a potential phi. So let's start with our game. So this is our game. And the algorithm will compute a bipartition of the game, which is like this. So this part here on the right, so remember that our game is assumed to be simple. So there is no simple cycle of weight 0. So this means that if you have a run on the game, maybe you can first see some weight 0s, but at some point you will have to see a non-negative weight, a non-zero weight. So then we can cut the game in 2 parts. There's the part from which the maximizer can ensure that the first non-zero weight that we see is actually positive. That's the part here on the right. And then there's the other part from which the other player can ensure that the first non-zero weight that we see is negative. And this partition here, it's very easy to compute it in linear time. So this is basically a reachability game. We know how to solve this. So that's easy to compute. Now, here, since max can ensure to see a weight which is positive and the weights are integral, then this means that the energy has to be greater than 1, because we can ensure that the profile has these small bumps at some point and goes higher than 1. And likewise here, the dual energy value has to be smaller than -1. Okay, and that's all we need. Because now we can define a potential to be 0 here on this side and 1 on this side. And this is really symmetric because up to shifting the potential, it's just like if we were considering the potential, which is 0 on the right and -1 on the left. So it's symmetric. And now, well, if we look at the drawing, what do we get? So our values are like this. So we have what do we know about our positive energy values? Well, we know that on this right part, they have to be greater than 1. So they look something like this. And we know that on the left part, the negative energy values have to be smaller than -1. And now we're defining this green potential, and it actually satisfies both potential reduction theorem and the dual, really by definition, because the energy is greater than 1 here and smaller than -1 here. So we can play on both sides. So that's the idea, and that's the algorithm. So we compute this partition, we define this potential, and we apply the reduction. So applying the reduction means we change the weight of the edges by decreasing by 1 all edges from right to left, increasing by 1 all edges from left to right, and leaving the other ones the same. This is what the algorithm does. And now, if you put all of these together, it's not hard to, and there's a few additional small observations to make, but it's not hard to derive this bound, which is really our main result. And second, well, okay, you have to work a bit more, but if you so this requires more work to obtain the combinatorial bound. And the proof here is really inspired by what Dorfman, Kaplan, and Zwick did. And you can end up with also the combinatorial bound in this algorithm. So this also requires adapting the potential a little bit. I'm not going to go into these details, but the idea is really this. Okay, so I'm done here. I hope that so all the details you can, of course, check in the paper. I hope that this conveyed some intuition. The take-home message is that this very old algorithm actually improves the state of the art. So that's quite surprising. And really, well, looking at it, we can get some very nice ideas for symmetric algorithms, and that's the real novelty in this work. Now, a question is, can we use this to actually compute values? So why I ask this question is because the current state of the art for the problem of computing values in the mean-payoff game is this bound, and it makes use of the value iteration algorithm that we mentioned. But now, since we have a better symmetric algorithm, maybe we can get a better bound for computing the values. So that's one open question. There are others. So I'm done here. Thank you very much for listening, and don't hesitate to go into the paper to read the details. Thank you.